This is going to be the second lecture on integration techniques. Integrals are very important to do, but there's no systematic way of doing them, so we have to learn various tricks. In this lecture, we're going to deal with two tricks. The first, which will apply to rational functions. Rational functions means one polynomial divided by another polynomial. And basically the method there will be, we shall decompose this into smaller pieces. We'll call them partial fractions. And hopefully each one of those little pieces will be possible to integrate separately, and then we add them all together. The second trick will be something that Richard Feynman, the great physicist, was very fond of. What this involves is that in the integrand, we either use a parameter or introduce a parameter, and then we differentiate inside the integral. This allows us to do integrals of various forms. So let's begin with the first. Let's begin with a simple fact of algebra. We're given this rather simple looking expression, 4 over x minus 3 plus 3 over x minus 2. And of course, we can write it differently. First, by taking the common denominator, which is x minus 3 into x minus 2. And then the numerator becomes 4 into x minus 2 plus 3 into x minus 3. Now, if we multiply out, we get 7x minus 17. And at the bottom, if we multiply out the factors, we get x squared minus 5x plus 6. So we've gone from something that's maybe a little simpler to something that's a little more complicated. Of course, they are exactly the same things, but now let's ask, can we work backwards? Can we go in the other direction? Why would you want to do that? Well, that's because this expression over here is in some ways easier to deal with than this expression over here. How we are going to do that is going to be the subject of the next few minutes of this lecture, and we are going to learn about partial fractions. Now, let's work backwards. So, 7x minus 17 divided by x squared minus 5x plus 6. So, we're starting off from this expression. The first thing that we want to do is factor the denominator over here. And the denominator is easily factored. It is, as you know very well, it is just x minus 3 into x minus 2. And so what we would now like to do is write this in the following form. As some constant, let's call it c1, divided by x minus 3. So one of the two factors, doesn't matter which order you write it. And then some other constant c2 divided by x minus 2. So we are now in a situation where we have two unknown constants, c1 and c2. Okay, so let's now take the common denominator, which is x minus 3 into x minus 2, and write this as c1 into x minus 2 and then plus c2 into x minus 3. So let me write this over here. We have c1 into x minus 2 plus c2 into x minus 3, and that's equal to the numerator 7x minus 17. So I have multiplied both sides of the equation above by x minus 3 into x minus 2, which is equivalently x squared minus 5x plus 6. And so we are now left with this equation over here, and from here we will find the values of c1 and c2. Now the easiest way of doing this is first put x equal to 2. If I put x equal to 2, notice that this over here this over here is 0, in which case I will have C2 into 2 minus 3, so in other words minus C2 equals 7 into 2 minus 17, which is minus 3, and so that gives us C2 equals 3. Now this equation is true for every value of x. Instead of putting x equal to 2, now I will put x equal to 3. So if I put x equal to 3, then this term over here goes away. And so I have C1 into 3 minus 2, which is 1. So C1 is equal to 7 into 3 minus 17. And that's 21 minus 17, which is 4. Therefore, I have got C1 equal to 4. And now that's exactly what I have over here, this 3 here, and this 4, of course, here is the 4 over here. The point is that we have now taken this expression and broken this up into partial fractions and therefore made this expression simpler. Let's now use partial fractions to evaluate this integral which is before you. So our first step will be to decompose or separate into partial fractions this quantity. And so I want to write it as C1 over x minus 1 plus C2 over x minus 4. And of course, we can take the common denominator over here, which is x minus 1 into x minus 4. And then we have C1 into x minus 4 plus C2 into x minus 1. And now we want C1 into x minus 4 plus C2 into x minus 1 to be equal to the numerator over here, this 1 over here. And so that's 1. Now the easiest way to find C1 and C2 is, let's first put x equal to, let's say, 4. In that case, this x minus 4 will be 0, and I'll have C2 into 4 minus 1, which is 3, equal to 1, and that gives me C2 equal to 1 by 3. Next, I'll put x equal to 1, and you see I've put the values of x looking at the denominators over here, 1 and 4. So now I have C1 into 1 minus 4, which is minus 3, equal to 1. And that gives me C1 equals minus 1/3. Now the important thing is that if we look at this expression over here, it has to hold for every value of x. And in particular, it will hold for x equal to 1 and x equal to 4. Of course, it will also hold for x equal to 0 and x equal to 23 or whatever. But we have made use of the fact that for certain values of x, we'll get a convenient relationship. And that's how we got C1 and C2. Well, now it's all very simple, because if I have dx of 1 over x minus 1 into x minus 4, then obviously this is minus 1/3, and the integral of x minus 1, 1 over x minus 1, plus 1/3 of the integral of 1 over x minus 4. And now we've done this earlier. The integral of 1 over x minus 1 is log of x minus 1. How do you know that? Well, just differentiate the log and you get 1 over x minus 1 over here. And of course, here we have exactly the same thing, except we have log of x minus 4. Okay, so that's the answer, but sometimes it's a little bit nicer to write this as log of x minus 4 over x minus 1. That's because log of a minus log of b is log of a over b. But this answer is fine. This is just a little bit prettier. Here's another integral that we would like to solve. The integrand is a rational function. Well, the numerator is just x to the power 0 or 1, and that's the simplest polynomial you can have. The denominator is x minus 4 into x minus 1 squared, and that's a cubic polynomial. We would, of course, very much like to write this as c1 over x minus 4 plus c2 over x minus 1 squared, where c1 and c2 are constants, but unfortunately this will not work. No matter how hard you try, you cannot find constants c1 and c2 such that the left-hand side and the right-hand side are equal. On the other hand, if you put a third constant c3 divided by x minus 1, then that will work. How did I know that there had to be 3 constants? Well, because if you look at the bottom over here, you have x minus 4 into x minus 1 into x minus 1. So 3 factors at the bottom over here, and that means we should have 3 terms here. Okay, so now let's make the common denominator, which is x minus 4 into x minus 1 squared. The numerator is c1 into x minus 1 squared plus c2 into x minus 4, and c3 will have both x minus 1 and x minus 4. Now our challenge is to find over here constants c1, c2, c3 such that this numerator, which I'm writing here, is equal to 1. This is a relation that holds for every value of x, and so it is my choice to make x have this or that value. Let me therefore put x equal to 4. If I put x equal to 4, you notice that the second term goes away and the third term goes away, and I have only c1 into 4 minus 1 squared, which is 9, and that's equal to 1. That tells me that c1 is equal to 1/9. Next, let me put x equal to 1. If I do that, then the first term goes away, the third term goes away, and I'm only left with c2 into 1 minus 4, which is minus 3, and the right-hand side is 1. That says that c2 is equal to minus 1/3. Now, what do I do about c2? Well, let me give x some other value, and of course the simplest value that I can think of is 0, in which case I will have c1, which is 1/9, into 1, and then I have 0 minus 4, so I have minus 4c2, and then I have to put in c3, which is 1/9, and there's 4 over there, and the right hand side is 1. This immediately gives me c2 equals minus 1/9. And so therefore we've succeeded in decomposing it. Now the only thing is to do this integral, and it's going to be very simple now, because the integral that we want is just c1, which is 1/9, integral dx over x minus 4, and then there's c2, which is minus 1/9, and that's this integral, and finally c3, and that's over x minus 1. Now this is logarithm of x minus 4. For the second integral, the answer is obvious. It's minus 1/9 into minus 1 over x minus 1. So it's 1/9, 1 over x minus 1. And the last one is C3, which is minus 1/9 log of x minus 1. And so you see that we have been able to solve this integral over here by decomposing it into three separate parts. This, and each one of these was separately integrable. Here's another integral, and the integrand is a rational function. There is a linear factor at the top, and there is a quartic factor in the denominator. That is 3 powers of x minus 1 and 1 of x minus 4. And we expect that there will be 4 terms on the right-hand side. So c1 over x minus 1 cubed and c2 over x minus 1 squared, c3 over x minus 1, and finally c4 over x minus 4. We expect these 4 terms because there are 3 factors of x minus 1 and 1 of x minus 4. Let's make the common denominator, and that common denominator is of course x minus 1 cubed into x minus 4. The numerator will have c1 multiplying x minus 4. Then c2 will multiply x minus 4 and x minus 1. c3 will multiply x minus 4 and x minus 1 squared. And finally, c4 will have x minus 1 cubed. The left side and the right side are going to be the same if we can find constants c1, c2, c3, c4. And so let's write that out once again. And you see that x minus 4 multiplies x minus 1 squared, and each power of x minus 1 is increasing as we go along until we reach c4. Now, we shall make an intelligent choice for x, put x equal to 1, in which case the coefficients of c2, c3, and c4 will all be 0, and we shall end up with c1 into 1 minus 4, which is minus 3, equal to 4 on the left side over here. Then, obviously, it would be a good choice to put x equal to 4, in which case the first, second, and third terms will all go away, and we'll only be left with c4 into 3 cubed, which is 27. That is equal to 7. And so we have c1 is minus 4 by 3, and c4 is 7 by 27. But what we do about finding c2 and c3? Now I could put x equal to 0 and then x equal to something else, but let's minimize our work. And we can do that by noting that on the left side over here, there is no x cubed. But on the right side, we're going to get an x cubed term from this term and from this term. So let's compare coefficients of x cubed on both sides. On the left side, I have 0, that is, there's no x cubed term over here. And on the right side, we have c3 into x cubed. So c3 into x cubed. And then there's also c4 into x cubed. But C4 is 7 over 27. And so from here, I get C3 is equal to minus 7 over 27. Now that's very good because we've got C1, C4, C3 with almost no work. Now we can find the remaining one by putting x equal to 0. In that case, 3 will be equal to C1. C1 is minus 4 by 3, so this is 16 by 3. Then we have 4C2. And then for C3, we have minus 7 over 27. But then this multiplies minus 4. So I have over here 28 by 27. And finally, C4, which is 7 over 27, multiplies minus 1. So minus 7 over 27. And now it'll take you just 1 minute to find out that C2 is minus 7 by 9. So we've got all the coefficients. All that's needed to find the integral now is the following. We need to simply write this out. This is the integral that we are solving for. And now there is C1. C1, as we look over here, is minus 4/3. And there's the integral of x minus 1 cubed. So I'm looking at this equation over here. Then I have C2. C2, as I can see, is minus 7/9. And then we integrate x minus 2 squared or x minus 1 squared in the denominator. Then there's C3, which is minus 7 over 27. And there's dx over x minus 1. And finally, the last term is C4, which is plus 7 over 27. And what's at the bottom is x minus 4. Now, each of these integrals we can do very easily. The first one, which is 1 over x cubed essentially, gives us 2/3 into 1 over x minus 1 squared. And that's because when we differentiate x minus 1 squared, we get minus 2 over x minus 1 cubed. So this integral is right. Then we have 7/9, and that multiplies 1 over x minus 1. And then the remaining two terms are simple logarithms. So this gives us log of x minus 1, and then the next term gives us log of x minus 4. So you see, we have a complete solution for this integral. It was just a little bit more complicated. The only new thing that I did over here was to compare coefficients of x cubed on the left and on the right. So you could say it's just a way of saving some trouble. We could do this whole integral just on one page using this little fact. So far we've dealt with integrals that have only linear factors in the denominator. Now we shall deal with those which have quadratic factors. Take this as an example. We can write x squared plus 4x plus 7 very obviously as x plus 2 squared. Now you see, the reason I take x plus 2 squared is that when I square it, I get x squared plus 4x plus 4. But I have 7 over here, so I must write this as plus 3. And now if we are told to write it as a sum of two squares, that's no problem because we can keep the first one as it is, and square root of 3 squared will be then the second number whose squared is to be added on. But what we really want is this integral. And so this is dx 1 over x plus 2 squared plus square root of 3 squared. Now, let me make a substitution. Let me put y equal to x plus 2. So dy is equal to dx. And so this is dy over 1 over y squared plus 3, or square root of 3 squared. And now let me make a further substitution. Let me put y equal to square root of 3 times, let's say, s. So then dy will be equal to square root of 3s. And so this is square root of 3. And now at the bottom, I have y squared, so that is 3s squared. What that means is I can take the 3 outside, and then this becomes ds 1 over s squared plus 1. Now we are in familiar territory, because the integral of 1 over s squared plus 1 we know to be just tan inverse s. So this is 1 over square root 3 tan inverse s. And now we can just keep substituting back. So this is 1 over square root 3 tan inverse s is y over square root of 3, and y is x plus 2. So we have x plus 2 over square root of 3. And so we have now found the integral, the desired integral, to be this value over here. We shall use what we learnt in the last example for this slightly more complicated integral. This has an x in the numerator, but the denominator is of course exactly the same. So we shall write the denominator as before after completing the squares. This is x plus 2 squared plus 3. And now I'm going to add 2 to x, but then also subtract 2 from x, keeping the denominator as it is. This now separates very cleanly into 2 parts. One is x plus 2 over the denominator, and the other is just a number over the denominator. And of course, our hope is that we can do this now easily. So let's look at the integral of the first part. That's x plus 2 over x plus 2 squared plus 3. And now let's make a change of variables. Put y equal to x plus 2 squared, because if we do that, then dy becomes 2 into x plus 2 dx. So this x plus 2 dx becomes half dy, and so this is half dy. And at the bottom, we have 1 over y plus 3. But that's easily done. That's just log of y plus 3. And we have already put y equal to x plus 2 squared. So when we open that out, that's half log of x squared plus 4x plus 7. That is the answer to this integral over here, which leaves us with this integral to solve. And so let's work on that now. So we have minus 2 dx over x plus 2 squared plus 3. But this is the integral that we just worked out. We know that the answer then is minus 2 over square root of 3 tan inverse x plus 2 over square root of 3. And so therefore, we have that the required integral is the sum of this and this. I need not write that out, but let's write it anyway. And so this is how we manage to get this final answer, which is a log and a tan inverse. Let me now summarize the general method of dealing with a ratio of two polynomials. Suppose we have f of x over g of x, where f is of lower degree than g. That means that at the top we can have something like this, let's say x to the 6 plus x to the 5 plus whatever. At the bottom we must have at least something like this, x to the 7th plus something further on. All of these are decreasing powers of x. In that case, in order to find this integral of f over g, we shall first break f over g into partial fractions. Now, partial fractions then make each term separately integrable, and then we just add the results. We've seen many examples of that. Again, let me reiterate. So here is a numerator. Here is a denominator which is of greater degree. You expand this out into partial fractions. Determine the coefficients a1, a2, a3, a4. I think I called them c1, c2, c3, c4 earlier. It doesn't matter. And then each one of these can be easily integrated. If you have something like this, on the other hand, where you have x squared plus 1 squared, in that case, you will expect, and we've talked about this, that this x squared plus 1 squared is actually x squared plus 1 into x squared plus 1. So you're going to have this term and this term, as well as, of course, this term. But now for something like this, x squared plus 1, you can expect that there will be a linear term at the top as well. Then it's a matter of finding out what a1, a2, a3, a4, a5 are. It's a perfectly standard practice. How you do it then depends on your cleverness. Choose right values of x, compare the coefficients of x on the left side and on the right side, I mean just the numerator, and use whatever tricks you like. Of course, there's only one answer, and so good luck on that. A very useful trick is that of differentiating under the integral sign. So let's say that we have some function f of x, and let's say that it's a definite integral from c to d. Then we would like the value of this integral, but we cannot differentiate with respect to x. And I stress that you cannot differentiate with respect to the variable of integration. Why? Well, if I look at this thing, this has no meaning because x is something that runs from all the way from c to d. And so you cannot say that this is a function that you'll evaluate at some value of x and then at some other value of x and take the differences, divide by epsilon, the way in which we have described derivatives to be. So this carries no meaning. On the other hand, let's say that f of x depends on some other variable or some what you might have thought is a constant. So for example, if I have f of x equals, let's say, 1 over x squared plus a squared. Well, then a is something that is to be considered as a variable, and then we can, of course, differentiate both sides with respect to a. And in that case, if I have something like this, f of x dx, then I can take the d by dA, so I can differentiate with respect to a, and take this derivative inside. So I have then d of f by dA, but integrated with respect to x. The fact that I can take the derivative with respect to a is obvious because f is assumed over here to be a differentiable function with respect to a, and so just changing the order of the derivatives and the integration is no problem in almost every case, except when functions are very badly behaved for some reason. So this is the basic idea of differentiating under the integral sign. We shall now take many different cases of this. Let's begin with this very simple example. The integral of e to the ax is equal to 1 over a e to the ax. Why? Well, because if I differentiate with respect to x, what I've just circled, I get e to the ax. However, now I'm going to differentiate with respect to a. What that means is that we can then take the derivative inside. So we take d by dA of e to the ax, that brings down an x. And if I take the second derivative, that is to say I do this once again, then I will get 2 powers of x. And obviously if I keep doing this, let's say I take the nth derivative with respect to a, and this is then going to give me integral of x to the power n e to the ax. But now let's look at this side. The integral of e to the ax is 1 over a e to the ax. And so what I have is this very nice formula that x to the n eax is then the nth derivative dn by dA to the n of e to the ax over a. And since taking derivatives is an easy thing, that means we've got all the integrals for all the values of n. All we need to do is keep differentiating once, twice, and just keep doing it. For n equal to 1, we have immediately that the integral x e to the ax is d by dA of e to the ax over a. And of course, you can do this differentiation very easily. We differentiate e to the ax, and that gives us x over a e to the ax. And then we need to differentiate the 1 over a, so that gives minus 1 over a squared e to the ax. And we can just simplify this a little bit by writing it as x minus 1 over a e to the ax over a. Now let's say that you wanted to put a equal to 1. You can do that now, having done all the derivatives, and you would get x e to the x is x minus 1 e to the x. Now that's exactly the formula that you got earlier using integration by parts. This kind of integral is very easily done if one thinks of the following trick. So instead of the integral up above, I'm going to look at this integral, 0 to infinity, e to the minus ax. Well, what is a? This is something that I've just put in there by hand. If I put a equal to 1, of course, I get e to the minus x. But you will see the advantage of doing this for any a. I'm taking a over here to be positive. In that case, let's just do this integral. It's very easy to do it generally. That's e to the minus ax over minus a. And if I put in the limits 0 to infinity, then e to the minus infinity is 0, e to the 0 is 1, and so I get 1 over a. Now, what if I differentiate both sides with respect to a, and immediately you will see that there is a real advantage to this. What I've found over here then is that e to the minus ax when differentiated gives minus x out there, and what we find then is that dx x e to the minus ax is minus d by dA of 1 over a, and of course that's just 1 over a squared. This minus sign, I repeat, comes about because of this minus sign in the exponential over here. Now we could do this again. So when you differentiate a second time what's above, then you will have the minus signs cancelling out, of course, and that's dx x squared e to the minus ax, 0 to infinity, and now that's the second derivative with respect to a of 1 over a. And that then, when you differentiate 1 over a squared, you get 2 over a cubed. And so that's 2 over a cubed. Now, imagine that I was to differentiate this again. In that case, you would get 3 in the numerator and a to the power 4. And you see that it's continuing in this way. 1 into 2 into 3 into 4, etc. Now put a equal to 1. So this is after the differentiation that we are putting a equal to 1. And so finally we get this very nice answer that after differentiating n times and putting a equal to 1, that this is equal to n factorial. You can see that for a equal to 1, looking over here, we have integral x e to the minus x is 1. Looking over here, you see that x squared e to the minus x is 2, having put a equal to 1 here. And in general, it is n factorial. This kind of integral is very easily done using the trick of differentiating under the integral sign. What we shall do as before is look at a slightly different integral. Look at, therefore, cosine of a times x. A is a parameter that we've just put in by hand. We can do this integral very easily. This is just sine of ax divided by a. And it has to be evaluated between 0 and pi by 2. At 0, sine is 0, so this is just sine of pi by 2a divided by a. Now let me differentiate the left side with respect to a. When I do that, then the d by dA goes and hits the cosine of ax, and when you differentiate cosine, you get minus sine, so minus x sine ax. You remember that I'm differentiating with respect to a, and so it is the x that comes out. And of course, this is between 0 and pi by 2. What if I differentiate what's above a second time? If I do that, then sine gets differentiated and gives cosine, and there's another x that comes out, so that's minus dx, x squared cosine of ax. Therefore, what we found is that the integral from 0 to pi by 2 of x squared cosine of ax is the second derivative with respect to a of what we have up above over here. So sine of pi a by 2 divided by a. And now we can work through this step at a time. So we have minus d by dA, and then when I take the derivative of sine, I will get cosine of pi a by 2 divided by a, and then of course I have to differentiate 1 over a, which gives me minus 1 over a squared, and sine as it is. One last differentiation, and when I differentiate cosine, I'll get sine. So when I do that, I'll get a pi by 2 again, but now it'll be squared because the cosine will give me minus sine of pi by 2, and so this is multiplying sine of pi a over 2 divided by a, and then we have to differentiate the 1 over a over here, which will give minus 1 over a squared, and so that gives 1 over a squared pi by 2 cosine of pi a over 2, and then finally we have to differentiate what's over here. When I differentiate 1 over a squared, I'll get minus 2 over a cubed. The sign shall remain as it is. And finally, we have to differentiate the sign, which will give us pi by 2 a squared cosine of pi a over 2. Now, put a equal to 1. So when we put a equal to 1, the left side becomes x squared cosine of x. The right side, you can see that when a is 1, all the cosines will go away. So this will go away and this will go away. And so the only thing that will be left will be sine of pi by 2, which is 1. And so we have pi squared over 4. And from here, we'll have minus 2. Of course, we could continue this, differentiate 2 more times, then we'd get the answer for n equal to 4, differentiate twice again, and we'll get the answer for n equal to 6. Clearly, this is a very nice, convenient way for doing this kind of integral. As our final example, we shall calculate this integral using the hint that maybe this integral has something to do with it. And indeed it does. Let's take the derivative with respect to a of what we have up above. So 1 over x squared plus a squared. And if I take d by dA inside the integral sign, then I get minus 2a divided by x squared plus a squared. Squared. And now, if I put a equal to 1 over here, then clearly we've got the integral that we want. Therefore, what we want becomes the following. It becomes just minus 1 over 2a, but a is 1, so minus half. And then we need to take the derivative with respect to a of 1 over a tan inverse x over a. And then once we've done the differentiation, then we shall put a equal to 1. We can't do it before that. So this is minus half, and now I'm going to differentiate 1 over a, which gives me minus 1 over a squared tan inverse x over a. And then I need to differentiate tan inverse x over a. That gives me 1 over a. I write this as before. Then 1 plus x squared over a squared. And then differentiating x over a, I get minus x over a squared. Now I can put a equal to 1, and this gives us the final answer, which is half tan inverse x plus half x over 1 plus x squared. So you see how well this differentiation under the integral sign worked out for this example. We now have a good repertoire of tricks. However, it's still not enough because we haven't really dealt with trigonometric functions very much, and we also have not as yet encountered hyperbolic functions. That's going to be done in the next lecture.